All right, folks. So we have the last part of chapter 17, which is the auditory part, the ear. This is all anatomy right here. I do want to point out one thing that you're going to be responsible for tracing a sound wave into the ear and how it works. And for this picture right here, you can see that the sound wave enters the external auditory meatus and hits the tympanic membrane. The tympanic membrane vibrates when that sound wave hits it, and that causes vibration of the malleus, which touches the incus and it vibrates the incus, which touches the stapes and vibrates the stapes. And then right here, the stapes is sitting on a membrane called the oval window, and it's vibrating that membrane. So now we're going to look inside, because when the stapes vibrates against the oval window and vibrates that membrane, fluid inside this vestibule and cochlea, this snail-looking thing is called the cochlea, and this is called the vestibule. Fluid inside there vibrates. Well, I shouldn't say it vibrates. The vibrations become a wave in this fluid, like the wave in an ocean, in fact. So we'll talk about how this wave travels through the fluid and how that lends to the sense of hearing. These are just a blown up picture of the three bones, the malleus, incus, and stapes. Two muscles are attached to these bones that protect your inner ear. And those two muscles are this tensor tympani muscle. What it does is if sound gets too loud, it contracts and pulls the malleus away from the eardrum, the tympanic membrane. In that way, the tympanic membrane is vibrating because sound is hitting it, but it's not transferred, that energy is not transferred to the cochlea. So that protects the cochlea. And another muscle right here called the stapedius, because it hooks to the stapes. That's why it calls the stapedius. That pulls the stapes away from the oval window, and in that way, it's the same thing that the tensor tympani does. It stops the transmission of the energy into the inner ear. All right, this is a tube within a tube body plan. You have to keep remembering that all the time. That's a tube within a tube body plan. What's going on here is you have this bony labyrinth right here. That's called the bony labyrinth. And then you have this membranous labyrinth right here. So the membranous labyrinth is the tube within the bony labyrinth, which is a tube. It's a tube within a tube body plan. And you can see that right here's the bony labyrinth, and right here's the membranous labyrinth. There's a fluid between the bony and membranous labyrinth, and that fluid is called perilymph. And there's also a fluid within the membranous labyrinth called endolymph. So this fluid is the fluid that's going to carry the vibrations, the sound wave vibrations in your hearing mechanism. All right, let's move on. Oh, by the way, before I move on, the sense of balance or position is going to occur here in the vestibule. This whole thing right here is called the vestibule. That's what that whole thing is called. And we have angular momentum that is detected in these ampulla. And the ampulla are the dilated regions at the bottom of the semicircular canals. So we'll blow up these ampulla, these crista ampullaris, that's what they're called. They're ampulla with inside, they are cristae inside the ampulla, so we call them cristae ampullaris. So we'll blow these up and see how you detect angular momentum. We'll do that. And then for linear motion, that's detected here in the utricle and saccule. Right here you have a macula or a spot, and right here you have another macula or spot. This is the utricle macule, and this is the saccule macule. We'll look at how these detect linear acceleration. It's not angular. It doesn't do angles or changes in motion. It just does linear acceleration and a static detection of where your body is, where your head is at that given time. So we'll look at that. Okay, there's nothing new here other than the nerve. The vestibular cochlear nerve is shown there. And we're going to blow those up and look at them. So let's do this right now. So what we're looking at here is the crista ampullaris. Let me go back and show you. So what we're looking at is these crista ampullaris right here. We're looking at these. Okay, that's what we're going to blow up and look at. This is going to be angular momentum. And it looks like this. We have this gelatinous material here called a cupula. This is pretty gelatinous. It's more viscous than the endolymph in which it exists. And we have these hair cells with cilia sticking up out of it. Stereocilia, they call it. And what happens is when your head changes when your head moves and changes its position or changes direction, this cupula either goes this way or this way. And when that happens, the hairs bend. They bend that way or that way. And when that happens, these hair cells fire and my vestibular nerve fires. So I have more details to tell you, but that's what basically is going on inside this crista ampullaris. Now let me go back and show you something. These crista ampullaris exist in three different planes. You know, if you had the XYZ plane, if you were to draw an X, a Y, and then a Z plane, these exist in that X, Y, and Z plane. You have this one going this way, and you have this one going this way, and then you have this one. I mean, one of these is coming in and out of the computer screen, or in and out of the board. Probably this one is coming in and out of the board. Oh no, probably not. I'm not sure which one they're trying to represent as coming in and out of the board, but these are in all three orientations, just as these semicircular canals are in all three orientations. So that's what's going on here. And by the way, the semicircular canals being in all three orientations, this endolymph is going to move. And when this endolymph moves, this cupule is going to move. So it's important that the three semicircular canals are in all three orientations. So there's the cupula, a gelatinous material. By the way, this is why you get dizzy when you're drinking, because alcohol diffuses into the endolymph, and alcohol diffuses into the gelatinous material of the cupula, and this becomes less viscous and moves more readily and bends these hair cells. So you feel like the room is spinning, but the room is not spinning. I mean, obviously the room is not spinning after you've had too much to drink, but it is because this cupula is bending and, for lack of a better word, flowing and bending these air cells. It's because alcohol did diffuse into that material. So this is the cupula. It's going to bend and bend these hair cells, and I have a picture to show you that. Right here I have the picture. So this is showing you direction of movement. So the endolymph inside the semicircular canals is going to move. This is the endolymph flowing down. It pushes the cupula down right there. That's the cupula being pushed down. And when that cupula pushes down, it bends these hair cells. That's what it does. When those hair cells bend, they fire. So this is showing you at rest, by the way, and this is showing you the endolymph flowing this way, and this is showing you the endolymph flowing that way. And of course, I have semicircular canals on three different axes, and I have these crista ampullaris in the ampulla of all of my semicircular canals. So I'm picking up all this information. Now, what I have here, this gelatinous material is the cupula, just so you know. What I have here is I have one real long cilium called kinocilium. It's a pretty long cilium. And then I have these stereocilia lined up out of this hair cell. All right, so I have one kinocilium, and I have stereocilia. Now, here's what happens. If the stereocilia bend towards the kinocilium, if the hair cell fires. If the hair cells bend away from the kinocilium, the hair cell hyperpolarizes. So this kinocilium is important in as much as the stereocilia either bend towards it and this hair cell fires, or the stereocilia bend away from it and the hair cell is inhibited. All right, so that's where the kinocilium comes into play. So that's how we detect angular momentum. We have the three semicircular canals filled with endolymph. The endolymph is going to flow, and when the endolymph flows, it makes the cupula bend. When the cupula bends, it fires this nerve and tells you which direction you're going. Now, obviously, when one direction is, when this is flowing and bending this cupula, then this is flowing. Then you can see this is flowing that way. So in one of the crista ampullaris, you'll have the stereocilia bending towards the kinocilium, and in the other one, they'll be bending away from the kinocilium. But it doesn't really, I mean, and that's important. It's important in as much as that my three semicircular canals are in three different planes, and I don't want to fire all three of them at the same time. I want some of them inhibited and some of them activated, so I know the reality of my movement, of my angular momentum. And that's what's going on with detecting angular momentum. The ampulla of my semicircular canals, the crista ampullaris. All right, now we're going to talk about this. I have this utricle right here, and I have the saccule right here. They're connected. I mean, the endolymph inside each can flow. All right, they're connected. But I have these spots inside the utricle and saccule, and these are called macula. That's where the macula are. These macula are going to detect linear acceleration, or static equilibrium, you could call it. And that is where your head is located in space, but not how it got there. So it doesn't detect how the head got there. It just detects, is it leaning forward? Is it leaning back? Is it leaning to the side, the other side? It detects that. And it can detect linear acceleration. It just can't detect angular momentum. Very similar to the crista ampullaris, except for there's stones in the gelatinous material. All right. These stones are called otoliths, and the gelatinous material is the top of my otolithic membrane. This whole thing right here is called my otolithic membrane. So my otolithic membrane is made of these supporting cells, these hair cells, and the neuron. And this gelatinous material is part of the otolithic membrane. My hair cells are embedded into it. Now, this gelatinous material is made heavier by these calcium carbonate crystals, these stones. These ear stones are calcium carbonate crystals. That's what they are, is calcium carbonate. When your head changes position, your crista ampullaris up here detect your head changing position. But after it gets to its new position, these stones will be pulled by gravity. And when these stones are pulled by gravity, they bend these hair cells. And these hair cells fire and go and tell your brain where your head is. So that's how this is going to work. That the stones are pulled by gravity, and they're embedded in the gelatinous materials. And when they get pulled by gravity, they bend the hair cells, and the hair cells fire. So that's what's going on with your static equilibrium or your linear acceleration. And this is showing you that happening. If I tilt my head back, the stone is pulled by gravity down towards the ground. It's embedded in the gelatinous material of the otolithic membrane, and it bends these hairs. So, and when these hairs bend, the hair cells fire, and the neuron fires, and it says my neuron increases its output. All right, so that's how I detected I tilted my head posteriorly. And if you tilt it anteriorly, the same thing happens. All right, so that's the macula of the utricle and saccule. All right, this is showing you from the vestibular nerve. Now, I know you learned the vestibulocochlear nerve, and that's fine. You know, it's fine. You remember the vestibulocochlear nerve. But it really is two different nerves in the beginning. You have just the vestibular nerve in the beginning coming from the vestibule, and that's carrying the information from the crista ampullaris and the macula of the utricle and saccule. And then you have the cochlear nerve coming from the cochlea, and that's your hearing nerve. They do fuse into the vestibular cochlear nerve. Well, where do they go? They go to the vestibular nucleus in the medulla oblongata. There's the vestibular nucleus. And from there, the information gets sent all over the place. For example, positioning of your head gets sent down the vestibulospinal tract to different muscles of your body. All right, they get sent there. Some of the information goes in your spinal accessory nerve, cranial nerve number 11. Just recall that the spinal accessory nerve goes to the sternocleidomastoid and the trapezius muscle. Those two muscles control your head position. So you send information to the muscles that control your head position. You send some information to your cerebellum. Your cerebellum wants to know where all parts of your body are at all given times. So information is sent to the cerebellum about the position and movement of your head. You can see that we send information up to the cerebral cortex. So the cerebral cortex can make a decision in what muscles to contract and how to move your body. We send information to the red nucleus of the midbrain, and you probably do remember this. From the red nucleus of the midbrain, I have a descending rubrospinal tract that goes to postural muscles. So we do that. I send information through the ocular motor nerve to the eyes. And by the way, my eyes move certain ways when my head moves. Why would my eyes have a certain consistent, repeated movement as my head moves? The answer is because as the position of my head moves, I send information up through my ocular motor nerve. I send information through my trochlear nerve, which innervates the lateral rectus muscle of my eyeball. The ocular motor nerve innervates the 4 of the 6 muscles of the eyeball. And by the way, the last cranial nerve that innervates the last muscle of the eyeball is the abducens, and that innervates. Oh, I actually screwed up right here. I think I said lateral rectus for 4. 4 is the trochlear nerve, and it goes to the superior oblique. I'm sorry about that. I think I misspoke on that. 4 is the trochlear nerve, and it goes to the superior oblique muscle. And I'm very sorry. I don't remember if I misspoke. I think I did. 6 is the abducens, and that goes to the lateral rectus muscle. So all of this information from the vestibular nerve goes to all these different places, and they help you stay in balance. Now hearing, all right? So we're going to talk about hearing now. Hearing has everything to do with this cochlea. And this is still a tube within a tube body plan, all right? So let me see which one is incoming. The purple arrows are the vibrations incoming. The sound wave hit your tympanic membrane, and from the tympanic membrane vibrated, which vibrated your malleus, which vibrated your incus, which vibrated your stapes. Right here's your stapes. The stapes is on the oval window right here. All right. The stapes is going to vibrate the oval window, and that's going to vibrate the perilymph inside this duct right here. And this is a tube within a tube body plan as well. This duct, it's really a straight duct. All right. And this is called the scala vestibuli. And this is called the scala tympani. And you're going to say they're the same tube, just rounded a corner. I would agree with that. I would agree that they're the same tube, they just rounded a corner. Here's the oval window. Your sound wave is traveling through here. It rounds the corner and comes back and hits your round window. So, and this is the cochlear duct right here. Cochlear duct. So I do have a straight picture of this for you, but my current picture I'm on right here is curled. So this straight duct is curled up to make this cochlea. It kind of looks like a snail. Well, my sound wave is traveling through here. You follow the purple arrows. Here's the purple arrows, the scala vestibuli, and you keep going around the circle. And then when you turn the corner, you're becoming orange, I believe. Yep, orange right here. When you turn the corner and you start going back out, now you're the orange arrow, and this is the scala tympani. And at the end of the orange arrow, you're going to hit this round window right here. And that round window is going to bulge because your sound wave has made a wave in this perilymph. The perilymph is going to bulge against the round window. Now, where is your endolymph? It's right in here. Your endolymph is inside this cochlear duct. Here's your endolymph in here. This is your endolymph inside this blue cochlear duct. So the perilymph is in the scala, and the endolymph is in the cochlear duct. All right, now I told you how the sound waves goes through this perilymph from the oval window to the round window, but I haven't told you how you hear yet. Getting there. This is the cochlea cut, and what you're looking at is the cochlear duct right here. That's the cochlear duct. This is the scala vestibuli, and this is the scala tympani. Remember, the scala vestibuli is carrying the sound wave inward, and the scala tympani is carrying it outward. Now realize I put these arrows here. I actually don't know which direction is inward here. Yeah, I can figure it out right here. So this is inward. I actually can't figure it out. I cannot figure it out. Okay, it doesn't matter. So the sound wave is going inward through the scala vestibuli, and the sound wave is coming out through the scala tympani. Now, some more anatomy that's important. There's a basilar membrane right here, all right? And on these basilar membrane, there's hair cells sitting right here. And these hair cells have hair sticking off of them. And the hair sticks off of them and sticks up into this tectorial membrane. The hairs stick up into the tectorial membrane. So that's what's going on there. And the hairs are bathed in endolymph. Now, endolymph is funny in one way. Endolymph actually looks like intracellular fluid. Endolymph is high in potassium and low in sodium. Extracellular fluid is high in sodium and low in potassium. Endolymph looks like intracellular fluid. And the endolymph in this cochlear duct looks like it's not intracellular fluid. It looks like it. Its composition is like it. Whereas the perilymph looks like extracellular fluid. It's high in sodium and low in potassium. All right, I'll come back to that. Now, as these sound waves travel through these sound waves can cut across, just so you know. They can cut across from the scala tympani to the scala, from the scala vestibuli to the scala tympani. They don't have to go all the way to the end and then back around. They can very easily just cut right through here. All right, the waves of those sound, the energy of those sound waves. I mean, it's the wave, it's the energy of the wave that can bend these membranes. So I guess I got to be clear there, more clear than I'm being. The sound wave has vibrated your tympanic membrane, which vibrated your bones, malleus, incus, and stapes, which vibrated your oval window, which then caused a wave in your perilymph. That energy in the wave of your perilymph can be transferred through here. It doesn't have to go to the end of the scala vestibuli around the corner and come back out through the scala tympani, although it can. That wave in the perilymph can go all the way to the end, but the energy can also be transmitted through here. Take a shortcut. When it's transmitted through here, these membranes bend, or they have a wave in them. They distort. The membrane distorts. And I have a picture of that for you. This is the cochlea cut like this. Like you can see this right here. It's cut like that. So you're looking at, and you're cutting, the picture is cutting all the way down through here. It's cutting like that. Let me see. Yeah, it's cutting this. So it's cutting this plane right here. And what it looks like when you get there is right there. Very difficult picture to look at unless you realize that unless you realize how you cut the snail. And this is what it looks like right here. So you're coming into and out of the board, and up in here is where you round the corner. At some point, you're rounding the corner right here. Okay? I can't think of anything else to tell you about this, so let's keep going. Now, this is how we hear. So what happens is you have this basilar membrane right here, and you have these supporting cells right here, and you have these hair cells embedded within the supporting cells, and these hair cells have hairs on them. And the hairs are embedded into this tectorial membrane. So I have a basilar membrane, and I have a tectorial membrane. When my basilar membrane distorts, it pushes everything up. My hair cells hit the tectorial membrane and bend. When the hair cells bend, this cochlear nerve fires. When the hair cells bend, this cochlear nerve fires, and it goes to your brain and tells you what kind of sound you're hearing. So that's how we hear. Those hair cells bend. All right, now I'm going to show you how the basilar membrane distorts. Well, before I get there, let's talk about the bending of the hair cells because I see what's coming next. So this is what it looks like. This is the hair cell, and these are the stereocilia sticking out of the hair cells. So this is a hair cell, and there's stereocilia sticking out of it, sticking into my tectorial membrane. So this picture right here is one of these blown up, actually the one in the box blown up. All right? Okay. This is how the hair cells bend. This is the hair cells at rest right here. What happens is this. I have this tip link right here. This tip link is shutting off that pore. When the hair cells bend, this tip link, this hair cell bends, and it opens that tip link. And then the cations in this fluid rush in and depolarize that cell. That's what they do. There is something very funny about the ear, and it's different than what you're used to. Similar to the eye that had a difference. Let me go backwards and remind you of something. Let me go backwards a little further so you can see it. This is the cochlear duct, which is filled with endolymph. All right? This is all the cochlear duct. That means these hair cells right here are bathed in endolymph. Well, as it turns out, endolymph is high in potassium and low in sodium. So when my tip link opens, what do you think rushes in? And the answer is what's on the outside. And what's on the outside, which is in the endolymph, is potassium, not sodium. So how I depolarize a stereocilia of my cochlea, of my organ of Corti, by the way, I should have told you that. This whole thing right here, I'm going back again, I'm sorry about that. This whole thing right here is called the organ of Corti. This whole thing right here is called the organ of Corti. The basilar membrane, the hair cells, the supporting cells, the tectorial membrane. Your book calls it spiral organ. That's why. I didn't see that word. It's also called the organ of Corti, or spiral organ. All right, so I forget what I was talking about. Yes, so the way you depolarize the hair cells in the organ of Corti is by potassium rushing in and depolarizing. That's how you depolarize the hair cells. Because it's the potassium that's in high concentration outside the hair cells, not sodium. Sodium's a very low concentration. There isn't even any sodium to rush in. So this is showing you the stereocilia at rest. The tip link is closed. This is showing you the bending of the hair cells where the tip link opens. The tip link, actually the blown up, I should be showing you up here. This is at rest. The tip link is closed. All right. This is when you bend and you open the tip link. You can see now potassium can rush through there. And this is showing you potassium rushing through there and depolarizing the hair cells. And as soon as you depolarize the hair cells, the cochlear nerve fires and goes to your brain. And of course, there's pumps, so you can pump that sodium back out. All right, so the sound waves, this is a tuning fork generating sound waves. The sound waves go into your ear and hit your tympanic membrane. When we talk about sound waves, we talk about a wave like this. A wavelength is the distance between one peak and one peak, or you can measure it between one trough and one trough. It doesn't really matter, it's the same distance, but that's the wavelength. All right. The shorter the wavelength, the more sound waves you can fit into a unit period of time. Let's see if I have a picture of that for you. No, I don't. You would agree probably that if I had shorter wavelengths, I could have another peak right here and another peak right here. And now my wavelength is from here to here, and from here to here, and from here to here. So the shorter the wavelengths, the more peaks or cycles I can fit into a period of time, a unit of time. I measure these I measure these wavelengths. Well, the wavelength is a distance, but I measure the number of wavelengths per period of time as cycles per second. That's what the number of wavelengths per unit of time, cycles per second. The unit of time happens to be a second. So how many of these waves in a second? That's what I want to know. How many in a second? So if you had 10 cycles per second, that's a higher frequency than 5 cycles per second. And 50 cycles per second is a higher frequency than 5 cycles per second. So how we perceive frequency is pitch. The higher the pitch, the higher the frequency. Or I should say it like this. The higher the frequency, the higher the pitch. We perceive this frequency as pitch. So a sound wave that has a real high frequency, a high cycle per second, comes in and vibrates the tympan membrane a lot of times in a second, and it vibrates the bones a lot of times in a second, and I get a wave in my paralymph that has very high frequency waves, and I perceive that as higher pitch. Now what about loudness? Well, loudness is just the amplitude of the sound wave. That's all it is amplitude of it. Because I could have a consistent frequency, but be louder, have a higher amplitude, and that's measured in decibels. The amplitude is measured in decibels. All right. So the amplitude is measured in decibels, and that's loudness, and the frequency is what we perceive as pitch. All right. And this just shows you the sound wave coming into the ear. The sound wave hitting the tympanic membrane and vibrating it, vibrating the malleus, vibrating the incus, vibrating the stapes, vibrating the oval window, vibrating the perilymph. All right, now I'm in the perilymph of the scala vestibuli. Let's go to the next page. So I'm vibrating the perilymph right here. It's going, it's going. It could go all the way to the end and round the helicotrema and come all the way back. It could. But the waves can also be carried across the organ of Corti. And when I do that, I distort my basilar membrane. When I distort my basilar membrane, whether on the initial distortion or the rebound, it doesn't really matter, I bend those hair cells. So you can see the energy of the sound wave crosses my organ of Corti, or my spiral organ, enters the scala tympani and heads towards the round window. I have a basilar membrane right here which is distorted. Now remember, when I distort that basilar membrane, I'm going to bend those hair cells, and they're going to fire. So this is the collage showing you that. And this is showing you with the cochlea unwound, and there's something else I want to tell you about here. The cochlea is unwound, so the sound wave can go through here. It could go around the corner and just head towards the round window. But the sound wave could also go through here and travel through the organ of Corti and bend this basilar membrane. Now, it doesn't matter if you're bending hairs at the initial distortion or the rebound. It doesn't matter, all right? But the hair cells are bent, and when they bend, they fire and the nerve fires. So I want to show you something else here. The length of these hair cells matter, because shorter hair cells are harder to bend, and longer hair cells are easier to bend. Well, higher frequency waves have more energy, and they bend shorter hair cells. So I have short hair cells in the beginning of my scala vestibuli, and I have longer hair cells towards the end of my scala vestibuli. Now remember, the hair cells are actually sticking off the basilar membrane. All right. So I hear the higher frequencies at the beginning of my scala vestibuli, and I actually shouldn't say it that. I shouldn't say it like that. I shouldn't say scala vestibuli. I have shorter hair cells in the basilar membrane in the beginning of my sound wave. I have longer hair cells in my basement membrane towards the end of my cochlea. So I really send a signal for high frequency sounds from the beginning of my cochlea, and I send information for low frequency sounds from the end of my cochlea. All right, so you can see the 16,000 hertz is high frequency and 1,000 hertz is low frequency. All right, this is a picture not in your book, but it's showing you the same thing. Now, what's it? Oh, it's saying something very important someplace down in here. Right there and right there. Sound waves that don't have enough energy to bend this basilar membrane here travel around the helicotrema and back out through. You really don't hear those. They don't have enough energy to bend the basilar membrane. But sound waves that have enough energy to bend the basilar membrane travel through my cochlear duct and bend the basilar membrane. The hairs bend and fire. So the sound waves have to have enough energy to travel through here. And if it travels through here, you're hearing high frequencies, middle of the road frequencies, low frequencies. The ones that go around the helicotrema, you don't hear at all. All right? So that's that.
Sound waves strike the tympanic membrane and cause it to vibrate. Vibration of the tympanic membrane causes the three bones of the middle ear to vibrate. The footplate of the stapes vibrates in the oval window. Vibration of the footplate causes the perilymph in the scala vestibuli to vibrate, which in turn causes displacement of the basilar membrane. Short wavelengths from high-pitched sounds cause displacement of the basilar membrane near the oval window. This movement is detected by hair cells of the spiral organ, which are not visible in the animation. Long wavelengths from low-pitched sounds cause displacement of the basilar membrane far from the oval window. Again, this movement is detected by hair cells of the spiral organ, which are not visible in the animation. When the vibrations reach the perilymph in the scala tympani, they travel to the round window where they are dampened.
All right, folks. All right, this is a table showing you the intensity of sounds. That's a decibel level. That's an amplitude of the sound wave. Remember, that's the amplitude. That's not the frequency. And it's just showing you with decibel levels when, it's really dangerous. So some damage occurs right here at 70 decibels. All right. But it does have to be continuous sound. I mean, if it's just brief, your stapedius and tensor tympani muscles can protect you. Look at this. Let me see. Alarm clock at 2 feet. Factory noise. I actually didn't realize an alarm clock at 2 feet was hurting you. Subway or factory noise. But you have to have more than 8 hours of exposure time. So, your alarm clock doesn't go off for 8 hours. For most of us anyway. Some of you guys might let it go off for 8 hours. Look down here at a gunshot or a jet plane. You have a gunshot or a jet plane. It's about 140 decibels. This is immediate danger immediately. There's no exposure time other than the very acute gunshot, and you can have damage right there and there. By the way, the danger is hearing damage, not the bullet coming out of the gun. I mean, that might be also dangerous too, but we're talking about hearing danger here. That's it. All right, so you can see these. You don't have to memorize this chart at all. It just gives you a sense of the decibels and when you're starting to hurt yourself. All right, the pathways. Lastly, the pathways. Now, we already did the vestibular pathway, but we haven't done the cochlear pathway. All right, so first of all, there's a superior olivary nucleus in the medulla. It's actually at the junction of the medulla and pons. We'll call it actually, what does this call it? Yeah, the pons. It's in the pons. So there's a superior olivary nucleus. Well, it kind of bothers me. It calls it the pons. It's at the junction of the medulla and pons. And you can see it is really the junction. It's starting to get fatter right there where the pons is. So right there, superior olivary nucleus, that's where the information initially comes in. All right. Then it goes up through and hits the inferior colliculi of the corpora quadrigemina. Remember, the superior colliculi right here do visual word just slipped my mind. Does visual reflexes, like you turn your head towards the sound, or you turn your head towards a flash of light. You turn your head towards a flash of light, and that's the superior colliculi of the corpora quadrigemina. And then the inferior colliculi of the corpora quadrigemina do auditory reflexes. You turn your head towards the sound. You hear a sound, you turn your head towards it. So the information from the sound goes to your inferior colliculi, and then it goes up through the medial geniculate nucleus. Now, remember what I told you a long time ago. I always think of this like this. Your eyes are medial to your ears, but your optic nerve travels through the lateral geniculate nucleus. Your ears are lateral to your eyes, but your auditory pathway goes through the medial geniculate nucleus. And that's how I have to remember it each time. After it leaves the inferior colliculi of the corpora quad, it goes up to the medial geniculate nucleus, and then from there it goes to the temporal lobe. The auditory cortex is in the temporal lobe. And you can see the mapping in the temporal lobe right here. Look at this mapping. I hear my low frequency sounds out on the edge of the lateral fissure. I hear my high frequency sounds in by the insula. Let me erase those writings and show you where the insula is, just so you orient yourself anatomically. Remember that this is the insula right here. That's the insula, all right? That's where you do gustation. This is the lateral fissure right here. This is my temporal lobe right here. This is my temporal lobe. You know that. Well, actually, I probably shouldn't put the dot up there because that's the parietal lobe. So this is parietal. This is temporal. All right. I hear right here in my temporal lobe, but I hear the high frequency sounds deep in my lateral fissure, and I hear my low frequency sounds out towards the surface of my lateral fissure. And that's kind of cool that we have a brain mapping where what receives what part. And of course, you know now that the short hair cells near the oval window send the high frequency sounds, and the long hair cells near the helicotrema send the low frequency sounds. And now you know where they go in the brain. All right, so that's the pathways. And that's it, folks.